Welcome to the third video in my series on statistics for sustainable development. In my last video, we saw how the concept of hypothesis testing can help us decide which of the children in our sample are stunted and which are not. If you've not already done so, you might want to watch that video first, and also video 1 on the normal distribution, links in the description. Today, we extend the idea of hypothesis testing to explore hypothesis testing for a mean. We will also introduce the t-statistic and the concept of statistical significance. We will be looking at this question: are our Ethiopian children different on average to the WHO growth standards? What is the null hypothesis in this case? We can state the null hypothesis as follows. Ethiopian children have the same mean height for age z-score as healthy children globally. The alternative hypothesis is that Ethiopian children do not have the same mean height for age z-score as healthy children globally. Let's unpack this. What do we mean by the mean? This statistic is often called the average and is calculated by adding up everybody's values and then dividing by the number of people in the group. So to find the mean height for age of all healthy children, we simply add up all their z-scores and then divide by the number of children. Assuming the distribution of healthy children is perfectly normal, then the mean z-score will be 0. In other words, exactly the same as the median. So we can re-express our null hypothesis to state that Ethiopian children have a mean height for age z-score of 0. We call this the hypothesized mean. We can now calculate the mean of our Ethiopian sample using the young lives data as before. We call this the sample mean. Recall that we have 1,906 children in our sample. If we add all the z-scores together, we get a total of about minus 2,036. We divide this by 1,906 and get a mean z-score of minus 1.07. We now need to test whether this sample mean is sufficiently low enough to reject the null hypothesis. For this, we need to calculate another statistic, which we can call the t-statistic. And we use this formula: t equals sample mean minus hypothesized mean divided by standard deviation over the square root of the sample size n. The top bit of the formula is easy, as we've already done the calculations. The sample mean is minus 1.07 and the hypothesized mean is 0. So the difference between the two is simply minus 1.07. The bottom bit, which we call the standard error, is a bit more complicated but still easy enough to calculate. As our variable of interest, the z-score, is already expressed in standard deviations, then the standard deviation of the population is simply 1. We divide this by the square root of 1,906 and come up with a standard error of 0.023, and hence a t-statistic of minus 47. So what does this tell us? Well, just like individuals from a population can be normally distributed around a median or mean, we can assume that the sample mean is also normally distributed. Remember that our sample contains fewer than 2,000 children out of a population of perhaps more than 2 million children of that age range living in Ethiopia at the time. We don't know the mean height for age z-score of the population, so the sample mean is our best estimate. But if we took a different sample from the same population, we would get a different sample mean. The particular sample mean that we've got is just one of many possible sample means that could be estimated from the population. If the true population mean of Ethiopia is a z-score of 0, then we would expect most of our sample means to be close to 0, with some coming out a bit above 0 and some being a bit below 0. In fact, statistical theory tells us that as long as our sample size is big enough, the sample means will be normally distributed like this. The question is our sample mean of minus 1.07 close enough to 0 such that we can accept the null hypothesis that the population mean is indeed 0, and it's just random chance that we picked a sample where the mean was a bit less than 0, or do we have sufficient evidence to reject the null hypothesis in favour of an alternative hypothesis that the population mean is not equal to 0? Well, we basically use the same reasoning as before. Just like the z-score tells us how many standard deviations in each individual child is away from the healthy median or mean, the t-statistic tells us how many standard errors our sample mean is away from the hypothesized mean. We can use the same rule of thumb as before. We know that under the null hypothesis, 95% of sample means will be less than 2 standard errors either side of 0. So a t-statistic of less than minus 2, or indeed more than +2, should lead us to reject the null hypothesis, and instead assert that in all probability the true population mean is not 0. Well, we found a t-statistic of -47, which is clearly a long way off the scale. Therefore, we can say with confidence that, assuming our sample is representative of the population, infants in Ethiopia have on average a height for age significantly lower than the healthy median. We use the word significant in the formal statistical sense, meaning that there is only a very small probability that we have incorrectly rejected the null hypothesis. As we've picked cutoffs of plus or minus 2, we can say that any result with a t-statistic outside of this range is statistically significant at the 5% level. We can see that for any given sample mean, as our sample size gets bigger, the standard error gets smaller, and the absolute value of the t-statistic gets bigger. So a bigger sample size helps us to get more precise estimates and makes it more likely that we get a statistically significant result. So what have we learned so far? In video 2, we saw that nearly a third of children in our Ethiopia sample are classified as stunted. And in this video, we saw that height for age is on average about 1 standard deviation below the healthy standard, and that this difference is statistically significant. The evidence suggests, therefore, that child malnutrition was a critical issue in Ethiopia at the time of this study. In my next video, we will begin to explore the factors that are associated with stunting in children and start to build a statistical model to help us identify some possible causes of malnutrition.